Hey guys, we're continuing on with our exploration of waves and wavelengths and whatnot. So we're going to start off with continue on with 25.4, which is wave speed. Wave speed's pretty easy because it's pretty conceptual, although there's an equation, but it's always easy. So let's go, like always, we'll write it up top here, just so we know what we're looking at. Always recourse. Oops. Wave speed. So it's pretty self-explanatory actually. It's really how fast the waves are moving. So if you're staring at a wave, and they give a good example just looking at, waves in the ocean. They're kind of moving in this pattern. How we looked at last video, this is called a transverse wave, and crest, crest, crest. Let me do this in different color. Crest, 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 trough, 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 and a difference distance here, distance here, distance, distance. It's called the wavelength, and the frequency is how many crests or how many troughs pass in a given period of time, often a second, and um, the period being how fast it takes for one wavelength to pass. And so it's pretty easy. But then we're looking at wave speed. Actually, how fast is it moving? Like, how fast are these crests and troughs passing by you? So they give that example of the bird, perched. He's kind of looking. So I'm going to just draw a face, kind of examining here. He's looking, and it's how fast they pass your eyes, and it's just speed. It's like moving, or velocity. If we look, it's a vector. It'll be a vector quantity, and so it's pretty simple. And the equation is wave speed, and this is kind of in the elongated form, and we'll condense it, is equal to the wavelength of the wave that you're looking at times the frequency of the wave. And we know how to find frequency already. So often this is a good way to find wavelength of a wave, because they may give you wave speed and they may give you frequency, or they may give you period. They may give you wave speed and the period. So wave speed and the period, and you could find the frequency if you have the period. So then you'd have to find wavelength. So again, period equals 1 over frequency, and frequency, oops, sorry, the pen is lagging a little bit today, equals 1 over period. So that's one way to find frequency if you want to find wavelength or wave speed. And then in the smaller sort of condensed form, you get v for velocity is equal to this, I think it's called a lambda. It's a Greek symbol. Frequency. So yeah, it's pretty simple. And yeah, lambda. There it is. I saw it right there. I was right. So pretty simple. Wave speed, not too hard. It's just plugging in equations. The real conceptual part is to visualize what speed is, but that's just how fast they're going past your eyes. So let's do a quick example. Mark off this little area. Let's say a wave has a wave speed of, what do we want to say? Let's say 3 meters per second. So 3 meters per second, and it has a period, kind of make this a little tricky, of, we want to say the period is 3 seconds maybe? Let's do 5 seconds. 5 seconds. I'm not sure how this is going to turn out, so don't hold it against me. And it asks, I'm making this up as I go. Find the wavelength. Wavelength. All right, let's mark off a little space here. And what do we know? We know wave speed, so let's start filling in our equation. We know wave speed. We know 3 equals wavelength. Trying to find. Let's denote that x. Okay? Or, of course, the lambda. Let's do that. That was stupid of me. And do we know frequency? We can find frequency. We're given the period, right? So let's go frequency equals 1/5 or 0.2, right? 0.2, and what's that? Hertz, right? Hertz. So then we have times 0.2. Now we'll do our good old algebra. 0.2 divided by 0.2, and we get lambda for wavelength is equal to, let's do a little calculator action here. Calculating this in my head. 15, right? Just multiply by 5 because 0.2 is 1/5. The wavelength is 15, and we're looking at what are our meters? Well, I mean, what are our units? Sorry, I gave the answer away. Our units would be meters, right? Because we have the seconds, we have meters per second, 3, and then we have seconds here. So the 2 seconds will cancel out. Sorry, I should have written meters per second and seconds. Seconds cancel out, we're left with meters. 15 meters. Pretty easy stuff. And this was kind of a difficult example because I didn't give you frequency, I gave you period. So you might get thrown that, in the future, so just be wary of that. Let's move on to the next couple sections. Really easy, 25.5 and 25.6 are the different types of waves. So let's go ahead and clear this so we can just talk about what we're looking at here. Alright, 25.5, transverse waves. That's what we've been looking at. That's the sine curve, that we've been, this kind of very generic looking thing. And this is the transverse wave. Transverse wave. So it's pretty easy to look at, and it's basically what it means is when the direction of the wave is going perpendicular to the direction in which the wave is moving. So let me read. I know I didn't explain that very well. Let me read from the book. Whenever the motion of the medium, I apologize, is at right angles to the direction in which the wave travels, the wave is transverse. So we see that the wave is traveling. Let's just say the wave is traveling this way. Okay, maybe it's traveling from the sun to the Earth, and it's going this way. Sun, Earth. Okay, so this is a light wave. Earth. Okay, and that's the direction of the wave. Now, if we notice the direction of the medium, the way the medium is moving is up and down, up and down, up and down, and it's not moving along in the same direction as the wave. So that means that the wave's transverse because they're at right angles, 90 degrees. So that's pretty easy. It's again the sine curve. And then for the longitudinal waves, waves like sound waves are longitudinal. The direction that the wave is moving is in the same direction as the medium. So it kind of looks like this, dense area of dense compression, then area of rarefaction, then compression, then rarefaction, and compression and rarefaction. You'll learn about that in chapter 27, I think. But you can look at it like this: crest, trough, crest, trough, crest, trough. So the distance between these crests or these troughs is the wavelength, and you can still find the frequency and the period based on the equations that we had, so you can still apply the wave speed equation and all that. So it's pretty much the same, but the two waves do have different properties that you learn about when we see light and sound. So I guess next video we'll talk about 25.7 through hopefully the Doppler effect, and then be done with chapter 25.